bad idea to review. Okay, so we're going to talk about axial and equatorial a little bit more. And you remember from the last section that if we have something that's pointing up and we demonstrate with a wedge, right? So this is what we call a wedge when it's shaded in, it's pointing up. If we have a dashed line like this, we call that a dash, and it's going down, dash for dash. Anyhow, so remember that when we alternate, when we go from carbons that are neighboring to each other in a cyclohexane, if you have one group pointing up, it's going to have to be up and axial, and on the neighboring carbon, it's going to be down and axial, right? Because up and down alternate, up axial, down axial is what I should have put there. And then if we flip the ring, so if we flip the ring, then the chlorine is still going to be pointing up, but now it's going to be up and equatorial, and the methyl is going to be going down, but now it's going to be down and equatorial. So remember, up is up, down is down, but up can be axial or equatorial. And remember, if two carbons are next to each other, if you have something that's up, the next thing is going to be down, and or something that's up and axial, the next group is going to be down and axial. So axial and equatorial, they alternate. So with this question here, it says draw both chair conformations for the following molecule and determine which one is more stable. So if I start by drawing a chair over here, do my best to draw a decent chair, okay? And then we're going to flip the ring, which is actually an equilibrium. This arrow that I drew here, that's nothing. I just kind of put that so you would remember flipping. All right, so if we flip the ring, then we're going to end up with the ring being flipped, of course, like this. Okay, so now, if the ethyl group is going up, and let's just assume it's axial, okay? Up and axial. And I'm going to number my carbons 1, 2, 3, 4, 5, 6. I'm going to start with this carbon here. 1, 2, 3, 4, 5, 6. It's just kind of the convention that the book uses. Okay, so if that group is up and axial, could anybody tell me, is the methyl group going to be up and down and axial or down and equatorial? The methyl group, will it be down and axial or down and equatorial? Can everybody hear me? Yeah, okay. So it's okay, is it going to be down and axial or down and equatorial? So remember, axial and equatorial alternate, right? Thanks, Eric. Right, so if the ethyl is going up and axial, that would mean that the proton here that's going down is down and equatorial, down and axial. And that would mean that the group here, the hydrogen that's up here, is going to be up and axial because axial alternates. Up, down, up. So if the hydrogen that I have in the green circle is up and axial, that means that the methyl is down and equatorial. So if I count over to carbon number 3, I'm going to put my methyl group in. So first I'll put my ethyl group in. So put CH2, CH3, and then my methyl group is going to be going down in equatorial. Notice that this line is parallel to these two lines. All right? So then if I flip the ring, my ethyl group is still going up, but now it's going to be up and equatorial. And my methyl group is going to be going down, but it's going to be down and axial. So if I change this, carbon 1, 2, 3, 4, 5, 6, on carbon 3, my methyl group is going to be going down like this. So could anybody take a guess as to which side the equilibrium is going to lie to in this case? Would it lie to the right or to the left? It's based off of 1,3 diaxial interactions. It's going to lie to the right side, isn't it, right? So if we fix this up, we'll put this arrow is going to be very small in this direction. Why? Because an ethyl group is larger than a methyl group, and the ethyl group is going to have diaxial interactions with these protons here, whereas the methyl group is going to have diaxial interactions with these protons here, but a methyl is smaller, and therefore it's more comfortable being in the the axial position. So this one is going to be the more stable of the two conformations. So we'll put here more stable. All right. And the very last thing I want to cover with you before we call it a day is the idea of cis and trans. And you might have covered this in general chemistry depending on who your instructor was. But the idea is that when you have a ring, you have two faces to that ring, right? There's the upper face and the lower face, right? Things are up and axial and up and equatorial. And then you have other groups that can be down and axial and equatorial. So if two groups are on the same face of the ring, we say they're cis to each other. And if they're on opposite faces of the ring, we say they're trans to each other. Nothing more than that. It says these two compounds, we call them stereoisomers. So that's the first time I've used that word in this class. We're going to talk about this a lot in chapter 5, but you do need to know the definition. Stereoisomers are nothing more than constitutional isomers, but and they can't be interconverted by a conformational change. So these two compounds have the same connectivity of their atoms, but they have a different arrangement in actual space. Okay, so it's actually in space is the only difference in the two structures. So if we were to draw the chair of the cis compound, you can see that since both substituents are up, I have one where this is up and axial, this is up and equatorial. And now when I flip the ring, this methyl group is going to be up and axial, and this methyl group is going to be up and equatorial. And so there's no difference in energy between this conformation and this conformation. They each have one thing up and one thing, or one thing axial and one thing equatorial. Whereas if I look at the trans, okay, in the trans, this conformation is going to be much lower in energy. Why? Because everything is equatorial, where in this one, everything is axial. And so you have a lot of 1,3 diaxial interactions. And so that covers the concept of cis and trans. Again, cis, two groups on the same face of the molecule. Trans, they're on opposite faces of the molecule.